Hi everybody. This is a short summarizing presentation of our paper of modeling and control of an omnidirectional micro-aerial vehicle equipped with a soft robotic arm. A lot of inspiration for robotics comes actually from the nature, and it was no different for the soft robotic arm. You can see the different dynamic maneuvers, which an elephant can do with its trunk. To reproduce certain parts of the trunk's capabilities, a soft robotic arm was built and modeled. A natural continuation of the development of the soft robotic arm was to free it from its fixed base, enabling it to increase its workspace. For this purpose, a highly maneuverable, fully actuated omnidirectional micro-aerial vehicle, or for short OMAV, has been chosen as the replacement for the fixed base. In theory, with a flying platform, the arm is now able to reach any point in the 3D space with any orientation. The main obstacle in the current endeavors in the soft flying manipulators is the too complicated model of the soft parts. To tackle this problem, and to enable real-time analytical control, we modeled the soft robotic arm with the Piecewise Constant Curvature, or PCC, and Augmented Rigid Body Model, in short ARBM hypotheses. This approach divides the continuum arm into different segments with constant curvature, and replaces each segment with a certain rigid robot equivalent representation. We chose a 7-joint rigid augmentation for the constant curvature segments, as you can see on the left. The OMAV is modeled as a fully actuated floating base. After the augmentation, the description reduces to a rigid body robot motion description, which can be then mapped back to the soft robotic space with special mapping Jacobians. To validate the model, we proposed a hierarchical controller, tailored for the platform. The controller consists of 3 tasks. The one with the highest priority is the end effector orientation task, then comes the end effector position, and then, finally, the OMAV orientation task. The task priorities should mirror their importance from the user's perspective. The lower level tasks are projected with a nullspace projector to prevent them interfering with higher level tasks. To test the capabilities of the platform and the controller, 3 simulations were conducted. The first one was to hold the end effector at a given point, with given orientation, while the OMAV's orientation was constantly changing. The second simulation was to show disturbance recovery abilities of the system. We applied a force to the OMAV, and then to the end effector. The third simulation was a circular trajectory tracking, with the OMAV always facing inside, towards the center point. The diagram shows the result of the disturbance recovery. It can be seen that the system is reacting fast, and returns to the target position after the disturbance vanishes. This wraps up the quick summary presentation. Thank you for your attention, and hope to see you at RoboSoft 22.